All right, so let's talk about what we did last time. We learned that the general amplitude for a scalar, master scalar EFT with just one type of abelian scalar can be written as some pole terms, some constant term, some term that is quartic in the momenta, corresponding to d to the 4, phi to the 4, something which is 6th order in momenta, 8th order in momenta, and so on. And we learned about the systematic expansion of this in terms of just symmetric polynomials in ST and U. This is specific for an amplitude with 4 identical scalars where there has to be exchange symmetry between any of them by Bose symmetry. Now, we also learned about EFTs and how the idea is that if I know some specific UV physics, I can low energy expand it, and I can get explicit results for these coefficients. And the example that we started out with is up there, and you can see how expanding that nice amplitude with your massive scalar exchanges leads to that low energy expansion with very specific coefficients. Now, if I want to think about going the other way, I start at low energy. I start with my most low energy expansion. Then whatever UV physics that might come from would be encoded into these coefficients. Here I'm writing them explicitly with some scale of the EFT, lambda, and some dimensionless numbers. These numbers, I don't know a priori, and pretty much they could be anything, I guess. But we parameterize this. These are basically the numbers that parameterize the EFT. I'm going to ignore the pole terms. They won't play a role for us here. So this could be things that come from phi cubed interactions. I'm also going to ignore the renormalizable phi to the 4 interaction, because that's sort of part of the renormalizable theory, and only focus on the coefficients, and why that is the case will become clear tomorrow. But I will only focus on these coefficients of the higher derivative operators. So what I should think about is that my low energy physics, this effective field theory, is parameterized by these dimensionless numbers in some units of some scale that I call lambda. Now, if I look at this, I could go back here, and I could multiply my amplitude by some number. It would change what the cubic coupling was if I had one. It would change what this one was. But otherwise, it would just scale all these guys by the same number. If I look at the amplitude in our example, that would basically correspond to changing what I call the coupling G squared. I could call it G squared times 2 or something like that. And it would still basically be the same theory. So a theory like this one in the UV completion, where I change the coupling G to some different number, is not fundamentally that different a theory. So I want to try to parameterize out that kind of rescaling. And so instead of just thinking about the EFT being parameterized by these numbers, I want to think about it in a way that we would call projectively. That means that I only really want to consider ratios of these couplings. And so we will consider ratios of couplings. And that is, again, to avoid this idea of thus rescaling the coupling G is not changing me to a fundamentally different theory. Okay, so now I'll define these barred couplings, GK, and these will be the usual GKs over on the other board, divided by the lowest one of these GKs. Now you might say, what if G2 is 0? Well, if G2 is 0, we clearly have to do something else. But maybe G2 is not allowed to be 0, as we will see. In fact, it is not allowed to, but that's not obvious at this point. Okay, so now my EFT has parameters, which is G3 bar, G4 bar, G5 bar, etc., etc. And it is these barred parameters that I want to try to place some bounds on. Now let's go and first get some intuition for the space of couplings by looking again at our good old example from the beginning of the first lecture. So here, I pulled out the thing that we would call G2, but now I have to write it in terms of this most general expansion in some units of this scale lambda. So let me multiply and divide by lambda to the 4th. So I pull that out. And then I can see that this is the term comparing to what I have down here, G2 over lambda to the 4. This object here, G squared lambda to the 4 over mass to the 6, is really what I should think of as the dimensionless quantity G2. I can separate that out into two parts. One is that my original cubic coupling G squared divided by mass squared. That's some dimensionless number, something. And then I have something that tells me where my mass is compared to the scale lambda that I use to characterize my EFT. Now, lambda I can think of as something that is just some reference scale. But if I think about what I'm doing in the EFT, if I map energy squared in this direction, then I have my massive particle m squared. It has some pole somewhere in that energy axis. And the lambda should be some scale that tells me that the EFT is valid below that scale. So that should definitely be below m, because I'm expanding, remember, in energy over over m. So my scale of validity, lambda, for the EFT should be somewhere below m. So this would be lambda squared. Aha. Okay, so that means that this parameter that sits here, lambda over m, in this case to the fourth, is some number that lies between 1 and infinity. So we see that lambda over, m over lambda should be something that at best could be 1, but in principle, m could sit arbitrarily high up compared to the scale below which my EFT is valid. So EFT description is down here below the lambda squared. It's the lambda scale. Now, I could go ahead and I could re-put back in the same way the lambda up here, but it becomes really annoying to have to vary m over lambda all the time. So for practical purposes, I'm going to set this lambda scale to be 1. So lambda equals 1 will be our reference scale for this. So I'm setting lambda to be 1. And it's just basically going to be a reference scale. So all the massive states that we have should lie above 1. Okay, now I can directly go over here and I can read off what the coupling should be by comparing the top board to the general board here. And we'll see that for the massive scalar, then my G2, sorry, I'll write a little bit bigger. My G2 is that quantity right there. G2 is G squared divided by m to the 6. G4 is G squared times 3 divided by m to the 8. And G to the 6, I'll write here, G to the 6 is going to be G squared over 2m to the 10. And of course, you can then go on for the rest of the expansion and figure out what everybody is. But what we really want to look at, as we talked about, is things scaled out, so projectively, so that we want to look at these bar quantities. And now we see from these couplings that what we get is that G3 bar is G3, so the 6, I think I wrote it wrong. This is G3, nobody said anything. This is G4, sorry about that. So G2, G3, G4. G3 bar is G3 divided by G2. So the G scale out, the G squared, which is what we want. We don't care what that number is really. And then we get a number which is 3 divided by m squared. And likewise, G4 bar will be 1 over 2 m to the 4 when I divide out by G2. Okay. Now, remember that my m squared is some number that I should take to be greater than 1. And now if I then combine these two things, then I see that I can think of G4 as being a function of G3 when I eliminate the m squared. And this function will be 1 over 18 G3 squared. Okay, so this defines some parabola. And if I now look in my space of these two types of couplings with G3 bar on the horizontal axis and G4 on the vertical axis, then I can draw this and say, aha, that means that as I vary m from being 1 up here to m going to infinity as I go down there, I will trace out this part of parameter space. Does that make sense? Yes. So I look at these couplings that I get from here by dividing G3 and G4 with G2. They're a function of m squared. If I solve this first one for m squared and plug back into G4, I will get that G4 bar is 1 over 18 G3 bar squared. Okay? And then I draw that and say in my coupling space, in my space of couplings that are traced out by this particular UV physics of just having one massive scalar, I get this line here, which is some parabola. Okay, that's what it is. That's what it is. And it goes, and I have to look at my scale, that the highest value I can get for G3 is 3, because as m squared goes to 1 up here, then I get 3 for G bar 3. And at the same time, the value that goes here on the vertical axis, the G4 axis, is going to be 1/2. Okay, so now I know that I have at least these parameters I know should be allowed in my space. What else could I possibly do to get a valid UV theory? Sure, yeah.
I'm not sure I understand like why we're defining here by D2. I guess it's just a
Good.
event in.
Good. So let me try to explain again. I will try why we do these barred quantities. So the reason is that if I look at the starting point up here, and I want to try to characterize theories that are different from each other. Okay? Then if I change the value of G to 1/2 G instead, then I don't change anything fundamentally in the fact that I integrated out a massive scalar. So I don't want these theories to lie at different points in my space. So I'm going to divide out by something that eliminates an overall scaling in the amplitude. So instead of characterizing my space of EFTs in terms of just the couplings, I characterize it in terms of ratios of the coupling. Does that make sense? And so now I'm looking in this space, the two lowest dimensional ratios of couplings that I have are G3 bar and G4 bar, and I say, okay, so this one theory that I looked at, where does that lie in that space? And what we want to try to understand is more generally is where am I allowed to be in this space? Can I be down here where both these couplings are negative? Would that be allowed? Right now we see that both of them have to be positive. I'm not allowed to make G3 negative. That didn't happen here. But could it be negative? The answer is yes, in principle it could be negative. But it certainly is not negative for this kind of model. Okay? Yes?
Do we care about an IR scale? Like how small we can make the energy scale of the theory to be?
So in some sense, picking this to be 1 is just arbitrary. It's just for me to avoid having to say, I'm going to vary ratios of m to lambda. And instead, I can just read off the coupling and say I'm varying m from 1 to infinity. We will talk about low energy spectrum later if that's what you're asking about. But otherwise, there's no IR that comes in here.
Quick here in the back.
Here.
I don't know if this is relevant in what we're going to discuss, but when you compute these ratios, I mean, isn't like taking care of the power counting being somehow more complicated than before?
Maybe. You can say, if this is a question about the power counting in the problem, you could ask, should I only compare couplings of the same dimensions? So I've done 2 things to eliminate scales. One is that I have looked at couplings that are only dimensionless by taking out this lambda scale. The other thing I'm doing is that I'm taking these ratios. So these are actually comparing couplings of operators with different dimensions, but it's also just comparing numbers. So the power counting there doesn't really matter. I'm not dividing polynomials with each other. I'm only looking at the coefficients. Okay. All right, so I had a scalar model. What if I have 2 scalars? All right, so now let's say that my UV theory is that I have 2 masses. One of them is, I'm going to write bigger, m1 squared, and the other one is m2 squared. And they're both scalars. And they could be the same mass, they could be different, one could be bigger, one could be smaller. There's my lambda scale, which I just set to 1, and then there's my IR physics down here. So my EFT is valid below that lambda scale. And I could pick these masses all the way down to lambda, or in other words, I could pick lambda all the way up to them. If I do that, then my amplitude will just be the sum of those two. So now I have, and I'll parameterize it in a certain way. I will take in shorthand the amplitude with the first mass plus the amplitude with the second mass. And then I'll give them some relative couplings, gamma. And gamma is some number that can vary between 1 and 0. Why should it only between these two values? That's because what gamma encodes is really two different versions of g squared. And that's a positive number. It's some real coupling squared. So I have to make sure that I always take positive linear combinations of couplings. Now, if I do that, then I can ask, as a function of m1 and m2, what do I get as I vary gamma? And so now I'm going to go back to my coupling space. This is G3 bar. This is G4 bar. Before, I had just one scalar, and it varied between G3 going from 0 to a half, all the way up here. And this was, let's think of this as my M1 mass. This was M1 being 1, and then M1 going down here, or M squared being 1. Now, that means that as I put in 2 extra masses, if I take, yes, go ahead.
So, because the field is real, then by neutrality, we expect the coupling to be real from a naive Lagrangian perspective of the normal G's. But now, because we're working with these ratios, I can cancel the I's basically. And now I'm a bit concerned unitarity.
No. So this is not a ratio of amplitudes. This is still just the amplitude. I can expand these, put in the low energy expansions, combine their terms, and extract the couplings, and then do the ratio of the couplings. But that still means that this guy is going to have to be positive, and this is positive by the same unitarity argument you gave.
Okay.
Okay, so this is not a ratio of amplitudes. This is the actual 4-point amplitude, just a linear combination of 2 different of the ones that we had up there. You take for each of them the low energy expansion. One looks like this with M1. The other one looks exactly the same with M2. But the G squared is basically now replaced with either 1 minus gamma or gamma. And then you read off the coefficients, and then you take ratios of them.
Right, so even the bar coefficients will still have to be real by unitarity.
They're still real.
Okay,
yeah,
okay,
absolutely.
thank you.
Okay, good. So this was with 1 mass. If I just think about having 1 mass, like M1, then I could say, okay, my M1, let's make it here. This is M1 squared. So this would be the case where I had gamma equals 1. Oh, 1, I mean 0. This is gamma equals 0. So I have the M1 amplitude, but I don't have the M2 amplitude. That sits there on a single scalar line. If I do the other one, let's put that down here. So this would be gamma equals 1. Let's say that the M2 is much bigger than the M1 that sits further down. Then that can sit there. As I vary gamma for fixed masses between 0 and 1, I'm going to trace out a line. That line will be something that connects these 2 points. And that has simply to do with the fact that this is a linear combination. It's linear in gamma. Even if I take ratio, it still just traces out a line in the projective space. And now you could see that if I vary the masses and then vary gamma, I can trace out the entire span of all these points, all these different points. As I change the masses, I could trace out anything in here, in this wedge. And that is the thing that would be called the convex hull of the original theory. That word is not so important unless you're a mathematician, I guess. But anyway, you can trace out this entire region. So anything in there, we would not be able to rule out as a sensible UV theory. That doesn't mean that anything outside it is bad, but at least everything inside there would have some, for this particular set of 2 couplings, some UV realization. Yes.
So when you write it as a linear composition that way, are you assuming that you're only dealing with non-interacting fields? Because it seems like if you have like a vertex.
Good. Okay. So what I mean by this is exactly and only taking two uncoupled, so two theories like this that otherwise don't talk to each other. The same scalar phi in both of them, but there's just two scalars, and they have two different couplings to the massless scalar. So there's a capital phi 1 and a capital phi 2, different masses. I don't care if they talk to each other, because at the leading order, this won't affect this amplitude at all, because it's just a tree-level exchange. Good, great. Okay, all right, so we just took that, and that means that every time you see these type of plots, what you get will always be some convex allowed region, because at least from the point of view of 4-point, I'm always just allowed to add amplitudes together, because they could come from things like different masses of different scalars or other things above. Okay, so now everything in here is definitely allowed. Now, what if I go a little bad and I misbehave and I say, oh, I forgot that I had to be unitary. I'm going to take gamma to be bigger than 1, or I'm going to take gamma to be less than 1. That would mean that my couplings were basically in my Lagrangian couplings in the G would be a complex number. So I would be very bad. And then you get some points that lie up here, or that lie down here, or you can even go negative. And so it might seem that maybe these are actually real bounds. If I do something that is non-unitary, I'm not allowed to be here. So maybe these are actual real bounds on these coefficients. That's a very tricky way to go that may or may not be true in certain cases. And we'll see here what is actually true at the end of the day. Okay. Now what it is that we're after in this case here is to understand much better, in much stronger generality, what kind of bounds one is allowed to get. And so we will ask questions such as, what is the allowed ranges, so the allowed values of these GKs, or width bars of each of the GKs. And so this general space where, because I draw it on a board, I want it to be some two-dimensional plot. So you can think of that as a projection of some other much bigger, higher dimensional convex space of all these ratios of couplings. And I just want to know what is the allowed region of those things. Now, there are two main approaches in the field to this. And generally, people call this the S-matrix bootstrap. But I'll specify it a little more specifically and call it the EFT S-matrix bootstrap, because there are so many things in the field that are now called bootstrap, and so many things that are called S-matrix bootstrap, but people mean completely different things by it. So this is the EFT S-matrix bootstrap. And even within that, people mean two different things. They may actually mean more than two different things, but two different things is that there's one called the Primal bootstrap. And the Primal bootstrap, the idea there is to rule stuff in. So you make an ansatz for a class of amplitudes you want to study that has the right properties. And then you check in your space, where can they be? It's basically what we just did now. We had some amplitude with massive scalars. We asked where are they allowed to be. We ruled some space in. But we didn't rule anything out. Well, yes, Carolina.
Sorry, do you have an understanding of what happens to the region if you allow an arbitrary number of scalars? Like,
no, sorry, if I put in more scalars, I don't get more.
You don't get more.
No,
it
in
stays
this case,
inside.
more is not more.
Okay, okay.
Yeah, yeah. In other cases, more gives more. But in this case, if I, okay, now I can't see it, but the behind the thing, this yellow region does not get bigger by putting in more scalars.
Bigger. Okay,
no.
good. Thank you.
Good. Okay, so Primal bootstrap rules in. What we will be concerned with is called the so-called dual bootstrap. It's not called the secondary bootstrap, as far as I know, even if the first is primal and dual, I don't know. Anyway, and the purpose there is to try to rule out Okay, so what is an example of ruling out? Ruling out is saying, okay, now let me think about my spectrum here. So this is my energy spectrum. And I have my massless states here. I have some cutoff scale, lambda c. And I will assume that there is some scale that allows me to put in a cutoff, which is not 0. So above 0, we call that a mass gap. Below which there's no massive states, there are no branch cuts, there's nothing. And above this, we're going to be completely agnostic. Not agnostic. Completely agnostic. You could have 1,000 poles, you could have 17 masses, you can scalars, vectors, massive spin 100, whatever you want. Branch cuts, don't care, as long as what it gives you is something that is unitary and obeys certain bounds on how fast the amplitude can grow at high energy. Has to be Lorentz invariant, locality, blah, 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 blah. We'll state all those conditions very clearly later. When you do that, then for this particular problem of bounding scalars, the most general dual bounds, oops, you guys have to remember this. For the most general dual bounds, it was found by Simon Cohen-Witt, who's here. Where are you, Simon? Thanks for not skipping the lectures on your work. It was found what that dual bootstrap region was. It's about 4 years ago. And here is the allowed region. So this is for G3 bar. And this is G4 bar. That upper bound we just found at 1/2 is a true bound. This guy is not allowed to get bigger. G4 is not allowed to get bigger. The bound we found from our quadratic relation between G3 bar and G4, namely 1/18 G3 bar squared, is a true bound. Anything inside is okay. Well, that's not exactly clear, but everything outside is ruled out. So this is a true bound. And then there's some funny bound over here. This is not to scale, by the way. There's some funny bound over here that looks like this. This is 3. This is about 10.35 or so with a minus in front, showing that this coupling G3 can go negative, but G4 is not allowed to go below 0. And I should maybe draw this a little more carefully to show that it goes up like this. Okay, that is there. We looked at the yellow region before, which was this entire region was spanned by our simple linear combination of scalar theories that we wrote down. And that tells you that anything out here has to have spin greater than or equal to 2. It turns out that no odd spins are allowed in this case, but anything that is in here with these parameters would have to have some massive particles with higher spin in the spectrum. Okay, now there are lots of things you can say about what is this and what spans that. We're not going to go into too many details about this, but I want to point out that this region has 2 special points where there are corners. And one of the things that we will be interested in these lectures is to understand better what corners means when you get these bounds. And I'll try to argue to you tomorrow why corners signify something important happening in the bounds. Okay, now let me make one thing clear. What is it that these bounds mean? They mean that anything inside this convex region, this is the good stuff, this is allowed in principle. But more specifically, it means that anything outside this region, any couplings you pick, somebody comes with a favorite EFT and say, look what I made. It has this coupling, it has this really negative G3, and it's really small G4. Isn't it a nice theory? And you're like, no, it's not a nice theory. It will violate either some bounds or it will violate unitarity. Go bad, bad, bad. Go find another one. Now somebody then comes and they come here like, look at my theory. And you check their couplings and it lies in the green region. Does that mean that there's a good theory? The answer is a maybe. Why is it a maybe? It's a maybe because whereas in this 2-dimensional projection of this whole allowed space, it looks perfectly fine. Their couplings may not be fine in other projections. That's one reason. So you'd have to check more to know whether it's a fine theory. Another thing that we don't have is that access to any higher point information. And higher point, together with symmetries, can create constraints at lower points. That's a very abstract way of saying it, but it's basically saying that we only have limited information here. So with the dual bootstrap bounds, we rule stuff out under the assumption that I'll give you very concretely later, but you don't always rule stuff in. To rule stuff in, you'll have to combine it with a primal bootstrap and see what can possibly span your space. Okay. Then there's a question. Yes, good.
Yeah, so if I start with an ansatz and I have a bunch of parameters that my ansatz depends on.
Yes.
And I try to rule out the parameter space that is not allowed. Would that be primal or dual approach?
If you make an ansatz, it depends what you make an ansatz for.
For the UV complete theory.
For the UV complete theory. So you make an ansatz for the whole amplitude that satisfies your symmetry constraints and your fall-off constraints and so on and so forth. And then you put it through some machinery to try to say bound EFT coefficients in its low energy expansion. That would be primal.
Right. Okay.
In the dual, as what I'll talk more about, I will make some assumptions, maybe some symmetries for the whole amplitude. But after that, I will just have the low energy expansion, and I will put in unitarity, crossing, constraints, such things to bootstrap it.
Okay. So even if I'm ruling some of my ansatz out, because I made an ansatz, it qualifies as a primal bootstrap.
Then I guess you're, yeah, in some sense, I would say that would still be a primal bootstrap. If some parameters had to be 0 or something like that, that would be some part of the parameter space, yeah.
Cool, thanks.
Yes, hi.
Hi. I don't know if you said it or not already, but is there something special about the region between the green and the yellow?
When from the dual bootstrap a priori, all these green things are equally good. You can start asking about where do different things lie in this space? Where do different types of theories lie? One thing you know is that if you're in the green but not yellow region, that you have to have some spin that is not just spin 1. So at this stage, that's all I will say about it. You can say more about where different, you can do more detailed analysis, but for this level, it's fine. Yeah.
Okay, thank you.
Good.
So one fundamental question I have is, why can we assume unitarity and these things of the UV theory? I know, like, we're just trying.
That's what we're gonna see. That's what so hold the question, because that's exactly the point of this.
Okay.
You won't, it's a priori from low energy. It's not obvious how this comes about. This is just showing you one result that comes out of doing that. But next I will start showing you what kind of input you need for it. Okay. All right. So now I'm going to switch gears a little bit from this initial example where we had full symmetry of the scalars to look at a model where we have a little less symmetry and in some cases a little more, but in a different way. That was very, very specific, right? Okay. Okay, so now let's think about having scalars that are not just some basic scalar theory. Okay, come on here. And there we go. So we're going to take and look at theories that could have complex scalars. So that will address some of the questions that some people asked about what if I had more than one massless scalar. So now we've got to combine 2 real scalars into a complex scalar. And I'll also give them a little bit more structure in that I will give them as part of some kind of gauge group or something like that. There'll be a color group or a flavor group. Whichever it is, doesn't matter so much, except that they have some group theory structure. So now we will look at complex scalars, ZA and C bar, let's call it A2, in the adjoint of some, and I'll put it in quotation mark. You can think of it as color, as in QCD, or you can think of it as a flavor group, whichever it is, doesn't matter so much. Some color group. Okay. Now, if you have such an amplitude, there will be generators of this color group entering the amplitudes, but the color structure and the kinematics part factorize from each other in a certain way. And I can write my tree amplitude of these scalars, this doesn't matter that they're complex, it's just about the adjoint, as something where I'll denote with square brackets the fact that I have pulled out a color structure. And so this is specifically for 4-point that I will pull out the trace. So here is one ordering of the trace. For the whole amplitude, you have to take all orderings of the trace. These are generators of my color group. And because the trace is cyclic, I only have to sum over permutations of lines 2, 3, and 4. So perms of lines 2, 3, and 4. Okay, so my amplitude with all the color structures included for 4-point at tree level can be written as this sum where I pull out color traces. What sits here is called the color ordered amplitude. And that is in itself a nice group invariant object, or in case of gauge symmetries, it's a gauge invariant object. And it too will have the cyclic symmetry so that this particular amplitude reflects the cyclic symmetry of the trace, etc.
Cyclic permutations or full?
Cyclic. So sorry, up here it's full. So you have 6 terms in total with all permutations of 2, 3, 4. But you angle the 1 because it would be anyway. That's because it's cyclic, right? But then the kinematic term that sits out here, that has as a symmetry that reflects the cyclicity of the trace that it multiplies. So it doesn't matter which order I put the lines in from that point of view, as long as it's cyclic with the first one. Okay, so now we do this. And the rule is that when you're dealing with color ordered amplitudes, the Feynman diagrams that you write down are not allowed to have any lines crossing, and you have to keep your order. Okay, so here it goes. I have some A4 amplitude with scalar. I keep the ordering 1, 2, 3, 4. I will do ZZ bar, and I put the square bracket around to indicate that it's nicely color ordered. There are 2 diagrams. I have 1, 2, 3, 4. And I'm thinking here of just, for example, exchanges with some massive scalar, just that we had before. That could be a real or a complex scalar. Sits there. And then I have another diagram with 1 and 4 together, like this. So I have S channel, and I have U channel for this. Okay. And this is also my scalar exchange. And one thing you notice is that the S channel, 1, 2, is on the same footing as the U channel, 1, 4. So it can be the same particle that gets exchanged. One of the things we notice is that there's no T channel, because T channel would involve 1 and 3, and I'm not allowed to interchange the ordering. It's my color ordered amplitude. I'm not allowed to cross any legs, so I cannot have any T exchange. And the other thing we notice is that these 2 diagrams I said were on the same footing. So this is SU symmetric in interchanges of S and U. Okay. Now, if I look at the low energy expansion of such an amplitude, then in general, not just specific to this particular scalar exchange, but in general, this amplitude with a pair of complex scalars, ZZ bar, color ordered, well, it could have pole terms. Well, let's write them down. 1 over S, 1 over U, no T channel. That would come from cubic interactions. Then I could have some constant term. Let's call that B00. That could be some term that multiplies the linear terms that we didn't have before, because before it was S plus T plus U, and because it had to be symmetric, but now it's just SU exchange symmetric. Then there can be some B20, S squared plus U squared. There can be some B21, which is SU plus da 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 cubic terms entering. Okay. Well, so that's my general low energy expansion. And if I took this to be a massive scalar exchanged, I could pull out exactly what these coefficients would be. But more generally, what I would have is that these BKQ coefficients are in one-to-one correspondence with derivative operators 2 to the k times z squared, z bar squared. So acting on this in that. So these are the coefficients associated with those operators in the effective action. Oh, there are two differences here. One is that I had the color ordering, and the difference is that they're complex scalars. So I mean, in some sense, it's not so different. I picked the complex scalars here just as a warm-up to we can do this, but otherwise, it would have been same for real scalars. It would also have had the same SU symmetry. Correct. That's correct. That's correct, as long as it's color ordered. Okay, and then the space that we would use to parameterize everything would again be these ratios. So we'd have some barred parameters, BKQ, divided by, let's call it B00. And those would be the one that parameterize the EFTs, just like we did before. Okay. Now, I could go ahead and then do the equivalent of this scalar theory. Was there some question? Hey, yes?
Yes. Is it obvious why do we have not t dependence in the local terms in the expansion?
I used the momentum conservation to write t as minus s minus u. Before, this eliminates redundancy by momentum conservation. But before, when we had STU symmetric polynomials, I didn't do that because then I would, after that, have to ensure that I was STU symmetric. Instead, I wrote things down that were explicitly STU symmetric, but then I had to worry about redundancy by momentum conservation. So here, I just eliminate that redundancy, and it's SU symmetric, so I just write that down. Okay. All right. Now, let's...
Sorry, quick question. In your BKQ Wilson coefficient expression, how does the Q relate to the operator, high derivative operator?
Who's talking? Sorry.
Yeah, sorry.
Hi.
Yeah,
Yes.
right behind you, it says BKQ, and then there's an arrow pointing towards the high dimensional operator.
The coefficient of this operator would be something that relates to BKQ. K labels the momentum order. Q would label how many independent operators there are of this kind, of that order. So for example, there's only one at this order, but here I have two. There's the S squared plus U squared, but there's also the SU. Both are allowed, two independent operators, and I use Q to label those. Thank you for asking that. Great. Okay. So let's go ahead and look at a specific example, which is very similar to our massive scalar from before. So I'll call it the single exchange or the scalar exchange amplitude for Z, Z bar, Z, Z bar. And it's actually just like before, but it just doesn't have the T channel. Oopsies, that's a plus. Okay, so this all the same as before, but now things are just a little bit different. I do the low energy expansion. I now have 2g squared instead of 3g squared divided by m squared. I have g squared over m to the 4 s plus u. I have no SU term because there's nothing in that amplitude that could possibly mix S and U together. So that is not there. But I have g squared over m to the 6 s squared plus u squared. And blah, 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 blah. And if I look at this.
Henriette?
Yes.
Before when.
Where are you? Here. Hi, Justin.
Hi. Before we ignored the linear and Mendelstems, or sorry, the consonant Mendelstems term, because we said it was a contact term.
Yes, but I'm not doing that now.
So, but why? Like we could have.
You're not allowed to ask that.
Okay.
because I will multiply this by something later that you know, and I will put that in. So before we ignored it, but I'm not going to ignore it now for reasons that will become apparent in a little bit. Thank you for being awake, as you should. Okay. All right. Sorry, you guys shouldn't be put off from asking questions. Justin is my student, so he's used to it. Okay, so this is B00. I ignored it before, but now I'm actually taking it seriously. I'll tell you why later. Okay, there's B10, which is this guy. And then this one is B20. And we learned that B21 had to be 0 because there was no SU term. All right, what does that mean in terms of these ratios of couplings? The what, sorry?
Here, are we ignoring the poles?
No, we're ignoring the poles also. Sorry. This one doesn't have poles in the low energy expansion because it didn't have a little phi cubed interaction to begin with. And in any case, I ignore the massless poles. They're important, but not for what we'll talk about today. Okay, so here are my coefficients. Now we compute the barred guys. B10 is equal to 1 over 2m squared as before the g squared nicely drop out. I again have my lambda to be 1. And then I have B20 bar, which becomes also 1 over 2, but now with an m to the 4. And if I eliminate the m squared, I'll see that the B20 squared, B20 with the bar, is related to B1 squared, but with a factor of 2 B10 squared. Okay, so now I can go to my space and I can draw what it looks like. Okay, I'll make it bigger. Here. This is my space. This is B10 bar. This is B20 bar. And now I can see, if I look at m going from 1 to infinity, that tells me that each of these coefficients go between 1/2, 0 and 1/2. So let's put 1/2 in. It's there. And if I take m to 1, then I'll be up here. And I'll have this quadratic curve coming up between them. That is allowed, ruled in. And just like before, I can say, aha, I can take linear combinations of these theories, and I can fill out the convex hull of all these points that were allowed. And now this wedge here is my allowed region. Okay, so that was a quick thing of doing something that was a little bit different from what we had before. Yes?
If I didn't have the UV amplitude,
Yes.
how would I discover that B21 has to vanish?
Oh, it doesn't in all cases. In general, B20, so B21 does not vanish. It only did for this particular UV theory.
Okay,
in general, it can be other values. Very good. Yes. Okay, so that was just in that example. And so here we have like a mini primal bootstrap where we ruled in a certain range, but we don't know whether we should take these bounds seriously or not. Okay, now the theory that I've introduced was a little bit of a warm-up case. The thing that I will bootstrap in all the remaining time is actually an EFT where I'll assume I have maximal supersymmetry in d dimensions. In 4 dimensions, which we'll be basically focusing on, that means n equals 4 supersymmetry. So I'll think about having n equals 4 super Yang-Mills with all higher derivative corrections that are compatible with maximal supersymmetry. And then I'll explain why that example that we just did here and worked through is very relevant for that study. Okay, so we will now specialize to our theory of interest. And we'll look at maximal supersymmetric EFTs. I want to do this without gravity, so my maximum massless spin will be 1. And so really this you should think about is that in 4D, this is, as I said, n equals 4 super Yang-Mills with higher derivative corrections, like that. Okay, so what is n equals 4 super Yang-Mills? Quick reminder, n equals 4 super Yang-Mills has massless particles, and they sit in some supermultiplet. It's Yang-Mills, which means that they're gluons. Because they're supersymmetry, they have partners. These partners are gluinos. Because there are 4 amounts of supersymmetry, there are 4 gluinos. And then to round the whole thing off, there also has to be 6 real scalars. These 6 real scalars we combine into 3 pairs of complex scalars. So that means that we have 3 pairs of complex scalars. And I'm going to pick one of those pairs and call it Z and C bar. And that's how it's going to connect back to the example that we just did. And one of those pairs I'll call C and C bar. Now, all these massless states live in the adjoint of the color group of the Yang-Mills. So they're all in the adjoint. And so that's also why our little warm-up example before was relevant for this case. Okay. So if I now look at the amplitudes in this theory.
Can I ask a question?
Point. Yes.
Hi.
Yeah, hi.
Sorry, can I understand why? Is it true that we can always write the 6 scalars in super Yang-Mills as 3 pairs of complex scalars? They have the same degrees of freedom, so I assume you can just always do that?
Yes, they're on
an
equal
condition?
footing. There is something called an R symmetry called SU4, which I'll assume is unbroken. That means they're all on equal footing. They transform into each other under that. So I can pick any one of the pairs, and they're all, from that point of view, on equal footing.
I see. Okay.
Good. Great. Okay. All right. So when you first hear lectures about amplitudes, people always like to tell you that gluon scattering is very complicated. You have to write this many thousand Feynman diagrams, but look, it's just one term when I write it in this very nice spin-helicity formalism. And that's true, but we'll not pursue that direction here. But I'll simply tell you this, that in n equals 4 super Yang-Mills, EFTs, well, not even EFTs, any theory with n equals 4 supersymmetry, I can write the 4 gluon amplitude in the following way. Supersymmetry requires it to be an amplitude that has 2 of the states be positive helicity and 2 of them be negative helicity. Again, I have all states going out. And just to recap quickly, these are massless spin 1 particles. They're characterized by helicity that can either be positive or negative 1. And so I have gluon 1 and 2 have positive helicity, gluon 3 and 4 have negative helicity. And it turns out that any amplitude at 4 point in such a theory can be written in terms of something called spin-helicity formalism, which I'll write once and for all, and then we'll not have to deal with it. If you know this, great. If not, then we will learn it another time, but take it for some input here. And then these brackets here, they really just encode the polarization of the vector, the massless vectors. And then there is some Mandelstam function that multiply this. And if you look carefully at what supersymmetry requires, then supersymmetry tells you that this function that you have here has to be symmetric in S and U. Now, it takes about at least half a lecture to go through the setup for supersymmetry and all the requirements, but that is essentially the part that we need. And this relation, that this function of S and U has to be symmetric in S and U, is really going to be important for us. Okay. Now, if f of s and u is the simplest thing you might think of, namely 1 over s times u, then what you get out from the formula I just wrote is the leading order Yang-Mills amplitude, the famous thing called the Park-Taylor amplitude. So this will, after some rewriting, give you the famous Park-Taylor amplitude for pure gluons. So this is just a two-derivative theory. The trace F squared theory has cubic quadratic interactions. You put it all together in your quantum field theory class. You calculate it and then rewrite it in some spinor helicity formula. And it's minus 1 over SU times those helicity factors up there. Now we want to look at higher derivative local interactions. So we want to look at interactions that are both gauge invariant. So they have to be made out of field strengths, F mu and U's. They have to be traced because it's a non-abelian theory. And then you can dress them up with derivatives. So the type of operators that we're interested in are called 2 to the d to the 2 k, f to the 4. And we want all such operators that are compatible with n equals 4 supersymmetry. Again, if we had to do this at the level of the Lagrangian, we would very quickly get very tired and go over and eat cookies instead, because even doing it for phi to the 4 is sort of annoying, but it can be written down. But even doing it for the lowest derivative operators, so you have to just think about all the ways you can place the derivatives, and now you have to use the equations of motion for all these fields. Now you have to use the SUSY relations and make sure that everything works. Nobody likes that. But what you know up here is exactly that I told you what the requirements of supersymmetry is. And that is that f is just a symmetric function in S and U. Yeah. What? Supercharge? You heard the word supercharge.
So I mean, it's n equals 4 supersymmetry theory, and yes. I just mean where is the supercharge? Did you ignore or something?
Oh, in this formula up here?
Yeah.
It's not a super amplitude. This is just a gluon amplitude.
Ah, okay. Okay.
Okay. So yes, you can write it in terms of supercharges, but we won't need that. Yeah. Okay. So what does supersymmetry do? Supersymmetry tells you that all the 4-point amplitudes are related to each other through some kinematic factors. And so it turns out that I can map directly from this gluon amplitude into an amplitude whose external states is a pair of one of these complex scalars. And if I do that, then long story short, I get a 4-point amplitude that I will write down explicitly here. Is now ZC, C bar, C bar. And it takes the form where supersymmetry replaces all this polarization, spinor helicity stuff with simply the Mandelstam variable S squared. So that sits there, and then it still multiplies this nice function, which has to be symmetric in S and U by supersymmetry. That now means that I can look at my EFT ansatz for this amplitude. So if I look at this EFT ansatz for this, I will have a term that is my usual Yang-Mills term that gives me the Park-Taylor amplitude. This will now be the Yang-Mills term for the adjoint scalars interacting, and they're exchanging. You can see there's only a U channel. They only exchange a gluon in the U channel where there's a C bar coupling, but a gluon cannot couple to the ZC, so there's no S channel. Okay, so that's what you get here. And then you get a sum over K going from 0 to in principle infinity, but let's cut it off at somewhere, at some K max. And then you get a sum. This comes over the derivatives in the interactions. And then this sums over the possible different terms that they could have. And then there are some coefficients that I call AKQ, and they multiply S to the K minus Q, U to the Q, and that is my most general low energy expansion. So it's very similar to the what I had up above. But you may notice that when I write here, this doesn't look like it has this SU symmetry. So the SU symmetry is what this thing in here has to obey. And in order to make it such, my coefficients, A, K, Q, have to satisfy what we call a SUSY crossing relation, namely that AK, comma, K minus Q has to be the same as AKQ. That ensures that this is symmetric under the exchange of S and U. That relation will be important. And if you look up here in my B expansion for our other trial case, you see that I have just already taken that kind of relation into account for the B's. Okay, I will say 2 more minutes, 4 more minutes worth of things. Okay. All right, and then that will round us off nicely. Okay, so this is the low energy expansion for the theory we want to look at. I will do a quick correspondence and tell you that the A00 coefficient here, that corresponds to the constant term in there, but it's multiplied by an S squared. So it's really something with 4 derivatives in it. What is the thing with 4 derivatives in it that is gauge invariant? That's really the F to the 4 operator. A10 corresponds to trace of D squared, F to the 4. A20 and A21 are 2 independent trace D to the 4, F to the 4 operators that are compatible with supersymmetry, and so on. And when I say it as F, it's because I'm really thinking of it in terms of the gluon scattering, but that's proportional to the scalar scattering. So this is also the same by supersymmetry as the D to the 4 Z absolute value to the 4th operator. Okay. Now, the goal will be to bootstrap in the dual sense these coefficients A, K, Q to try to find bounds on this higher derivative expansion, assuming as little as possible low energy information. Now we can already do something based on the example that we had before with a massive scalar. And I think, is that what's hiding underneath here? It's exactly what is hiding underneath here. Because you can imagine that if I took the massive scalar amplitude that I will write now in yellow, I take an example. The what, sorry? The mass will be a massive scalar that I integrate out. So this is an example. So let me write it down. It is exactly the same as before. I imagine that I have a massive scalar that I couple to this in some supersymmetric way. I claim I can do that. This is symmetric, so it obeys all my SUSY rules. It has the S squared. It obeys all my SUSY rules. It's exactly the same as we had with the B coefficient, just with an S squared now. And that is the reason why I didn't ignore the B00 coefficient, as Justin pointed out, because that corresponds now to my A00 coefficient. And now I can replace everywhere here A from the B's. And I will get exactly the same type of relations as before. And I will get the same amount of allowed space as in the other example. The fact that I have an S squared out in front doesn't matter for the low energy expansion. It's just that I translate the coefficients. So this is all the allowed range of my scalar theories when I linear combine such things in this way. Now there's one thing I just want to make a point out here at the end. And that is when I first set up the B amplitude, I took Z, Z bar, C, Z bar. And I argued that it was equivalent from the point of view of the S channel and the U channel. So therefore, it had to be an SU symmetric amplitude. Now I have claimed that supersymmetry tells me that this amplitude has SU symmetry. But I also argued that there was no S channel pole. There was only a U channel in the massless case in this expansion up there. So how could it be that an amplitude that has different sets of states in the S channel and in the U channel could possibly be SU symmetric? I could let you sit with that, but I will tell you, in this S channel, what we have here is a scalar exchange. But in the U channel, what is exchanged is something that knows about S squared here. We'll learn about next time what that means. That means that up here in the U channel is a linear combination of a spin 0 and a spin 2. Why should that possibly have the same coupling as the spin 0 here? The answer is supersymmetry will guarantee that and requires that. Okay, so that maybe is a little bit of a subtle point. It's not so important for the rest of it, but I just wanted to point it out. What we're going to do next time is we're going to talk about some general properties of amplitudes. We're going to derive what I call dispersive relations for these AKQs and derive some general bounds and then specialize them and try to bootstrap the open string from that. Okay, that's the end of today.
Okay, any final questions? One here.
I mean, in your full theory, you don't have a spin 2, right? Didn't you just?
I can have a non-self-dual n equals 4 massive multiplet with a spin 2
with the
all
mass.
the way down
Okay,
to 0.
Okay.
Correct.
Sorry, got it.
Yes. Yes. Good.
Sorry, I think I missed the part where the segment you drew in is the primal, in the yellow. Is that the primal bootstrap, or is it the is it ruled in or is it ruled out? Sorry.
This is a very low class primal bootstrap where I just look at these scalar type of exchange amplitudes of this form and linear combinations of them, and I ask where do they lie.
Okay.
And what we'll derive next time is the actual dual bounds.
Okay.
Yeah.
Nice.
Great.
Okay, if that's it, then we'll be back at 4.
All right.